So we will do common base topology today. So we finished common emitter, and now we will do the common base topology. So we will see what is the difference and why common emitter is mostly used for amplification and not common base. Okay. So for common base, what will happen? That this, one second. Okay. So the input will be applied to your emitter and the output will be taken from the base. Okay, that is common base. Okay, so this is your transistor. Here in the emitter terminal, the input Vin is applied. The base is biased with a DC source, and this is your supply. This is RC. From here you are taking the output. Okay, so this is the input, the emitter terminal, and this is the output. So we will find out what the input impedance is, Rn. We'll find out Rout. We'll find out AV. Okay, the voltage gain. So whenever we see in a common base, we will see it from here. So what is the value of resistance looking into the emitter terminal of the circuit? Then looking into from this terminal, we see Rout, right? And V out upon V in will give you AV. Okay, so I think this much is clear. Okay, so what is our next step? So let us draw the small signal equivalent. So before that, you must know that if there is any change in V in delta V, if there is a change in V in delta V, it will result in a corresponding change of current, right? So the current will change by Gm times delta V. This is the current that flows, right? So if that is the current that flows, then what is the drop here? The drop is Gm delta V RC. Okay, so now as this delta V increases, that means the drop across RC will, what will happen? That will also go up, right? So now you see that so this is the response of the CV stage to a small input voltage. Okay, so now if the if the collector current goes down with Gm times delta V, okay, because if there is an increase of delta V in the in this input voltage, then the collector current will go down by delta V, right? For an increase in the input, the collector current goes down, and if the collector current goes down, then the drop across RC will go down, and if the drop across RC goes down, the V out rises, right? So the relationship is that if V in rises, V out also rises. So this is a positive relationship, right? And you will see that V out will be nothing but Gm times delta V into what? RC, right? For an AC ground. So you see now that for a corresponding change, so delta V out by delta V, if I say, okay, if I say a delta V out, then it comes Gm RC. So automatically, yes, the gain is, voltage gain is Gm time RC, which is same as the common emitter, right? So, and also we are getting it in the same phase. So basically the voltage gain is same as the common emitter, right, with the same phase, 0-degree phase shift. And so why don't we use common base? Why use common emitter then? So we will see that it boils down to the impedances. Okay, so let us draw the small signal equivalent. So the small signal equivalent is similar to what a common emitter is, right? So this is your small signal equivalent. If there is Va is not infinity, R naught will be present, and there will be Gm V pi. and this will be your V out. From here the collector terminal V out is going on, and here you remember we had VB, a DC source, so that goes to short. This is R pi plus minus V pi, and here in the emitter terminal you have the input. Okay, so this is basically your the small signal model, and if there is a collector resistance present, then RC. Okay, so now here if you apply KVL, KCL, whatever you want to do, if you solve this circuit, you will get V out upon V in as GM-RC. Now after this, let us now start with the input impedance and all calculation. So one more thing is, so there is one more topic that was of concern, if you remember, which is the voltage headroom concern, right? Voltage headroom of this kind of circuit. So let's see what is the voltage headroom of this circuit. So this is your circuit. Okay, this is VB, VCC, RC, right? So now assume that Vin is at 0 volts. Okay, the DC bias of this point, because this is the emitter also needs a DC bias, right? So let's say that the V in DC is at 0 volts. Okay, so now what is the minimum that VB has to be? VB has to be 0.8 volts, right? So VB has to be 0.8 volts, so that this comes to be 800 millivolts. Now we know that for this circuit to be biased properly, that VBE has to be 800 millivolts and VBC has to be less than 0, right? So if VBC has to be less than 0, that means VCB minimum value will be greater than equal to, so let me not write greater than equal to, the VCB minimum is 800 millivolt. Okay, so VCB minimum is 800 millivolt. So here I am putting VCE minimum is 800 millivolt. VBC and VCE minimum is 800 millivolts. So this is 800 millivolts. Okay, minimum value. It has to be greater than 800 millivolts. It cannot go less than 800 millivolts. So there is a dissipation of 800 here. Okay, that automatically has now limited the output voltage. Right? So the output voltage swing has automatically decreased. Okay, so there is a headroom limitation. Okay, so this limitation, because V out will be equal to VCC minus whatever is the drop across RC, right? So I can write VCC minus VBE can be the drop across RC, and this is what is actually going to limit my V out as well, because the drop across RC has to be less than equal to that. Okay, so after this, now let us solve a design problem. Please write down this question. The voltage produced by an electronic thermometer is equal to 600 millivolts at room temperature. Design a common base stage to sense the thermometer voltage and amplify the change with maximum gain. Assume VCC equals to 1.8 volts, IC equals to 0.2 milliampere, and IS equals to 5 into 10 to the power minus 17 ampere. Beta is 100. Okay, so this is a design problem of common base stage. So please note this question down. I'm giving you 2 minutes for this. Okay, so I hope you have written down the question and you know how to use the value of IS, right? I have told you in the previous classes. So the first point will be that uh, you are given the 600 millivolt voltage that is being produced, right? So now what is the circuit look like? So this V is what is coming from the thermometer, okay? And here is VB, V out, okay? So this is your overall circuit. Now what will be VB? What is VB? You see this voltage is automatically getting defined by the VBE and V in DC value, whatever is getting sensed, right? So 0.6, okay? So VBE plus 0.6. So I can write this as VT natural log IC upon IS plus 0.6, right? You are given IC 0.2 milliampere, IS, so 2 into 10 to the power minus 3, and IS is 5 into 10 to the power minus 17, right? So please put in the values. So VT you take it as 26 millivolts only. Yeah, so 26 millivolts or 0.026 volts. So please see what VB you are getting. Okay. Please calculate. Okay. So since you have joined, you should do the calculation. Okay. So VB will be 0.026 natural log of 0.2 into 10 to the power minus 3 upon 5 into 10 to the power minus 17 plus 0.6 giving you 1.35 volts. Okay, so VB is 1.354 volts. Okay, one first thing we have got. Now to avoid saturation, okay, because we need to bias it in the amplification region, right? So to avoid saturation, this collector voltage that I had mentioned earlier, that VCB should be less than 0. So the collector voltage must not fall below the base voltage, right? So therefore what will be the maximum voltage drop across RC? Maximum voltage drop across RC will be VCC minus where you have put the VB, right? Earlier just in the just before I have explained you. So 1.8 minus 1.354, which is 0.446 volts, right? So now you have the drop across RC, you know IC, which is 0.2 milliampere, and therefore from here you have RC, which is 0.446 by zero point 0.2, giving you 2.23 kilo. So please look into the question till here, whatever we are doing, and then we will proceed. So basically we are doing this because we have to find, we have to design the CB stage, right? So we are finding voltage gain and then we will see how we are proceeding with the design, okay? Now, you always remember that whenever we see a stage something like this, from where is the VB coming? We have to bias the base, right? So just like we saw in the common emitter configuration, we were doing the biasing with the help of a resistor divider network. In common base also, the similar kind of thing can be done. Okay, so now since you have RC, you can simply find AV, which is GMRC, and GM is IC by VT and into RC. Okay, so please put in the values and check what AV you are getting. IC is 0.2 milliampere. This is 26 millivolts, and RC we got as 2.23 kilo ohms. So take care of the units. Okay, please take care of the units when you are solving. So if you solve this, you will get 17.2. Okay, so now next, since this is a design problem, okay, so this will not come as a design problem in gate, it will come as a normal numerical. They won't ask you to design the circuit, or they will give you the circuit, then simply ask to get the values out of it. So this is sorry. Excuse me. Yes, so here we know that now if this is VB, then what is VB? It is R2 by R1 plus R2 into VCC, right? Okay, so now you have VB, you have VCC, you will therefore have a combination, right? So now we know that beta is 100, and for lower sensitivity, if you remember that for lower, so let me write this, okay? We have done this in when we were doing the common emitter. So for lower sensitivity of the circuit to beta, we generally keep I1 as 10 times IB, right? I1 is usually kept greater to IB by a factor of 10. Okay, so now with this, if you solve, so if I1 is 10 times IB, that means 10 times IB is what? IC by beta, 10 times 0.2 milliampere by 100, 20 microampere, right? So now what is I1? I1 is nothing but VCC by R1 plus R2. Considering IB is very small, so VCC by R1 plus R2 is nothing but 20 microampere. This is the first point. The next point is that this one VB, right? So VB is R2 by R1 plus R2 into VCC. So can you now solve it? So I'm putting everything in the screen will actually shorten it up. So VB was 1.354. So just let me just write it. So VB we found 1.354 and VCC is 1.8. Okay. So now can you solve it? Please solve these two and tell me what R1 and R2 you guys are getting. So I'm waiting for you guys. Okay. I'm giving you 5 minutes. Please solve this. please solve this. Tell me the answer. Okay, so I'm not getting any response from any one of you. So let me just see. Okay, 1.8 upon R1 plus R2 is equal to 20 by 1000, which is in milliamperes, right? So from here you will get R1 plus R2 as, I think it is 90 kilo ohms. Okay, and then substitute it. So 1.3, sorry, my internet is poor, so it is getting disconnected from the iPad. Okay, so 1.354 equals to R2 upon 90 kilo ohms into 1.8, right? So from here you will get R2 as 90 into 1.354 divided by 1.8, which is 67.7 kilo ohms is R2, and therefore the R1 from here will be 22.3 K. Okay, so this is your answer this for the design problem. Okay, so basically I took the problem to just show you that it is the same way that we have done the biasing of the emitter stage from the resistor biasing, we can also bias the common base stage as well. Okay, okay, so let's now start with the next thing, which is the impedances of the common base. Okay, so calculation of Rn and Rout of CB amplifier. So before that I will show you how intuitively also you can find out the Rn and Rout value, and you won't need to make the small signal model for that. Okay, so how we have drawn the circuit? What was the circuit? The circuit was this. Okay, right? So the AC ground, there is AC ground. So this is an AC ground, and I am finding the Rn from here. Okay, so now intuitively if I say that, okay, you know what, I had this V in here, and the V changed by delta V. Now what is Rn? Rn is nothing but delta V by delta I. So if the input changes by some amount, then what is the change in the current supplied by this input, and that ratio gives us the input impedance, right? So if there is a change in the voltage by a amount delta V, if there is a change in the voltage by amount delta V, then Rn is given by delta V by delta I. Now intuitively you see, okay, what happens when this voltage is changed by delta V, the current is also changed by delta V, Gm times delta V, right? So now the current has become Gm times delta V, and this same current is flowing into the impedance as well, right? It is, everything is in series, right? So therefore delta V is the voltage change, is delta V in. So delta V is nothing, delta V in is nothing but delta V. And what is delta IN? Let me just write it in opposite way. Delta V in is nothing but delta V, that it changes the voltage by delta V, and because of that there was a change in current Gm times delta V. This is the change in current. So now Rin is nothing but what? Division of the two, delta V in by delta In, which is giving me 1 by Gm. So intuitively, without drawing the small signal, we are getting 1 by Gm. We will draw the small signal as well. We will see when we draw the small signal what comes. But intuitively, you can see that this is how we can get like a simple input impedance. Now with this calculation, you can compare with the CE stage. So please first see whatever I have written. So what I have written is that if there is a change in the voltage V in, and because of this that change, there is a proportional change in the current, right? uh, so that change, increment or decrement, let us not go into that. So if delta V is the input change, there is a current change of Gm delta V, and that same current is entering the input as well, right? It is the same path. So therefore that is the current change from the input source. So therefore, the division of this change in voltage to that of the change in current will give me the input impedance, and that is how I come up with 1 by Gm. So please have a look at it. I am giving you 1 minute. Have a look at it, and then we will also solve it through small signal analysis and check if things are coming. Okay, I'm giving you 1 minute. Just look at it. Okay, I think you have understood this. So this is the basic Rn, okay, of the common base stage. Rn is 1 by Gm. What is R out? R out will be nothing but, looking from here, R out will be R0. Looking from here, it is Rc. So R out is basically Rc parallel R0. Okay, and now we will see from the small signal analysis how things turn out to be. But before that, we will see the voltage gain. Okay, so let us see how the voltage gain can be calculated. Now suppose there is a series resistance Rs, okay, which will be there in common base configuration. We normally use the Rs concept, the series resistance concept, okay, so which is there. So now I have to find out the voltage gain. So looking from here, you know that this impedance is 1 by Gm, is it not? This is 1 by Gm, right? So if I find in this point, if I find the voltage gain, then if I apply the series voltage division rule, I will get my AB. So this node is, let's say, Vx. Okay. So what is Vx? Vx is nothing but 1 by Gm. by 1 by Gm plus Rs into Vn. I hope this one is clear, right? Because the no, so how do we got 1 by Gm? Just now I showed you, right? Rn is 1 by Gm, and Rn is nothing but this impedance looking from this terminal, right? From the emitter terminal, because emitter is the input for common base. So Rn is the impedance looking from the emitter terminal. So this is how you got it, right? Now what is V out by Vx? V out by Vx, we found out it was GMRC, right? The actual voltage gain. So now it is pretty easy. V out by Vn is therefore nothing but Gm times Rc upon 1 plus GMRs, because this will go to Vx equals to 1 upon 1 plus GMRs. I think this is pretty clear. This is a very simple thing. So from here and here we get this one. Okay, and this is an important conclusion, that the actual, if the series resistance is present, then what we get in the voltage gain is a decreased version of the original voltage gain. So in actual, if you remember the common emitter thing, in that also the impedance is the one which used to come in the denominator, and here you see that Gm times Rc is no longer the voltage gain. What is the voltage gain is the Gm times Rc upon 1 plus GMRS. So basically because of the presence of series resistance, the value of voltage gain has decreased. Okay, so today I will be taking a 2-hour session. It is already displayed in the NPTEL thing. So 4 to 6, in between you can have a 5 minutes break. So we'll finish all the CB and CC, and then we are done with the entire BJT amplification thing. Okay, topic. Okay, so please have a look into whatever I have done till now, and then we will proceed from here. Okay, so now let us find the this thing, the input impedance and output impedance with the help of small signal model as well. So I want you to solve the small signal model as well for this. Okay, so how will the small signal model look like? We just saw it, right? So let me draw it. The base will be AC ground since the presence of VB, because of the presence of VB. Now you see that when I talk about input impedance, I talk about the impedance looking into the terminal. Okay, so I have not considered any RE here for now, right? Because even if RE is present, even if there is some resistance present, what I am saying is I am seeing the Rn from here. Okay, I am seeing the Rn from here. So this is Rn. Okay. Okay. So now this is V pi. Please see the polarity. See the direction of current. I think it is not clear. This is the direction of current. Okay. So what will be V in upon In? You have to put a, you can put a KVL and KCL both you have to see. So this is In. Okay, and from here GMV pi is coming. Consider R0 as infinity. Okay, so very small amount of current is going that way to have a simplified solving. So this is the current which is In plus GMV pi. I hope till here it is clear. Uh, there is no rocket science here. It's pretty simple, right? So now put a KVL. Put a KVL from here to this ground. Okay. So what is the KVL equation? Vn equals to In into, sorry, In plus GMV pi into R pi. This is my first equation, right? Now you see in this there is three unknowns, V in, and V pi. But you need to find R in, which is V in by In. So in this equation, what you have to do, you have to omit V pi. Exactly, right? So first what I did, I first draw the circuit, right? For a simplified version, I took R naught to be infinity, VA infinity, so R naught infinity. Then I just marked the currents. See, okay, so then in the emitter branch, it is In current is flowing. I am getting a GM V pi current from the collector branch, and In plus GM V pi is what will therefore go to the base. Now V pi I have to replace. So how will I replace V pi? So there is one more simple KVL which is put here, which is Vn equals to minus V pi. Just check. So in the same branch, if you don't consider the drop across R pi in terms of current and resistance, if you consider it in terms of V pi, Vn is coming as minus V pi. This is equation 2. So now please solve and tell me what Rn you are getting. Okay, I am waiting. So I have done the derivation here. Please check. Okay, and please do the derivation. Okay, so just check it and then we'll proceed. Please have a look into the entire derivation once, then we will proceed. So can you please start solving the for the output impedance? You have to put a DC and IDC VDC source at the output, and IDC will be the current. Okay, and everything else will be AC ground. So please start it, and then I will solve the small signal and do it. But before that, you guys please start. So I have drawn the small signal model for the calculation of output impedance. The ratio of VDC by IDC will give you R out. So please start. You have to consider R naught here. Okay, we will see how the R naught effect comes. So please, because we are looking into the output impedance, we should consider R naught. Sorry, R naught. And if you don't consider R naught, what will happen? We will see. Okay. So please start solving and find out VDC upon IDC. I'm giving you 5 minutes for this. It's a bit calculative, but you will get it. It's not that difficult. Please solve. 2 more minutes. It's pretty easy. Just put a KCL and KVL in proper nodes and paths. You will get it. So after we finish solving this, for the output impedance, we will have a look into the voltage gain, solve some problems, and then we will go to the common collector. Okay. Okay, so let's please, if you have solved, please let me know, or else I will solve it. So let's do it. So you see that in this node, the current IDC is entering, right? So what is leaving from here is also IDC. I hope this concept is clear, right? So now what goes inside RE are two currents. One which comes from here and one is from here, and that goes to RE. Okay. So now with this knowledge, let me just put KVL and KCL equations. Okay. Let me see if I'm able to come up with something. Hmm? So one is at this node A. So at node A, okay. What is the voltage at node A? VA is nothing but minus V pi. You can check. VA is the voltage with respect to ground, right? And the voltage at VA with respect to ground is nothing but what? V pi in a negative way, right? So minus of V pi with respect to ground. Okay. So now I'm putting the KCL. So minus V pi upon RE minus V pi upon R pi. These are all outwards currents equal to GMV pi. Okay. And another one will be so if I take a inward current, oh sorry, this will be IDC equal to IDC. Okay, so minus V pi upon RE parallel R pi is IDC. How did I get that? Because if you take V pi minus V pi in common, what is in the bracket is 1 by RE plus 1 by R pi, which is nothing but equal to 1 upon RE parallel R pi, right? So this is what I have written. So this is my equation 1. Please have a look. Tell me if you are missing something or you are unable to understand. I'm giving you 1 minute, just have a look. Now let me erase this part. Okay. So now the another one is, what I want is VDC by IDC, right? So R out will be equal to VDC by IDC. Now I can put a KCL here, or I can put a KVL equation. So let me go with a KVL equation. So KVL equation is minus VDC plus IDC minus GMB pi into R naught minus V pi equal to 0. So therefore VDC equals to VDC plus IDC R naught equal to minus V pi 1 plus GM R naught. 1 plus GM R naught. Please have a look into this. I put a KCL. I did not do anything else. I just put a KVL to this path. I should not draw it like this. Let me draw it with some other color. Okay. Put a KVL in this path. Okay. I hope it is visible. Just look, have a look at it. So can you guys now solve it? What you have to do is you have to find out the value of V pi from equation 1 and you substitute that in equation number 2. I'm giving you 5 minutes for this. Please solve it. After that we will again resume. So uh, I'm giving you a 5 minutes break. So in within 5 minutes just solve this thing. Okay, find out V pi from equation 1, put it in equation 2, solve and get VDC by IDC. Okay. So after 5 minutes, let us resume and we will take the class till 6. So I hope you have got the answer. Okay. Okay, so let me just do whatever I was asking you to do. So from equation 1, hmm, VDC plus IDC R naught equals to, we'll write in terms of IDC. So 1 plus GM R naught into RE parallel with R pi into IDC with a negative sign. This is what you will get. So now if I take all the IDC to one side, am I missing something? The negative sign is there. Oh, so this will be positive, I guess. There should be one positive sign. This will be positive, right? So VDC plus IDC are not. Okay, there is one sign mistake here as well. This will be VDC minus IDC R naught. So for it, sorry for this. This will be VDC minus IDC R naught. You can check. Okay, so minus VDC plus IDC minus GM pi R naught minus V pi is 0. So I have taken all the V pi term to right side. So minus V pi 1 plus GM R naught, and here I have written VDC minus IDC R naught. That is the second equation. Okay. So now VDC equals to IDC. If I take common, I get R naught plus 1 plus GM R naught into RE parallel R pi. And this is my R out. R out is nothing but VDC by IDC, which is nothing but equal to R naught plus, right? And if you remember, how did your circuit look like? So this is an important result. Okay, this is your common base. Now if you try to find out the output resistance R out, okay, so what we right now found out was this resistance R out dash, let's say. Okay, so when you are doing that, in that process, what you have to first do is AC ground. So when you do the AC ground, this is RE, this is grounded, and this is grounded, and I'm looking it from here. So basically the entire R out will be RC parallel to R out dash, right? And what I'm getting R out dash as, I'm getting R naught plus 1 plus GM R naught RE parallel R pi, which is nothing but a similar result to common emitter degeneration, right? This is a similar result to common emitter with degeneration. Now how did it happen? If you see, the R naught is nothing but a resistor between here, right, from collector to emitter. This is what my R naught is. Now R naught, and what RE is doing, it is basically degenerating, right? And therefore, as of the rules of the degeneration are that it is multiplied with the resistance which is degenerating, that gets multiplied with the gain factor, and gets added to the original output resistance, and that gives you the total output, the total resistance. So that is what has exactly happened. Okay, so this is a very interesting result. Please take a note of this. Okay, so now after this we will see how the voltage gain gets affected with the presence of base resistance. Okay, so please take a note of this. Please take a note of the entire solution. I'm giving you 1 minute. Please take a note of entire solution. We have 1 more hour of class left, so we'll try to finish off the entire chapter today. So common base with common collector. Okay, so now let us see what happens when there is a presence of RB. Okay, base resistance is present. So when base resistance is present, let me draw the small signal model. Now in this case, what you see the voltage at Vp, it is nothing but V out upon beta Rc into Rb plus R pi. Now how did it come? So we are considering Va as infinity, okay, and Rb is greater than 0. So this is the case, okay. Now what is V out by Rc? V out by Rc is nothing but minus GM pi. This can be our first equation. Okay, so from here you will get V pi. V pi is minus V out by GMRC. So let me just write it. V pi is minus V out by GM times RC, right? And therefore, what is VP? What is the voltage VP? VP is nothing but the voltage V pi and the drop across RB, right? So the current flowing through R pi and RB is therefore it will be equal to V pi by R pi, right? So basically that current, let me say IB is nothing but equal to V pi by R pi, right? So RB is nothing but equal to minus V out by GM R pi RC, and therefore IB is equals to minus V out by beta RC. First thing, right? So now what is VP? VP will be nothing but IB by RB plus R pi. Sorry, IB into RB plus R pi is VP. Please have a look into whatever I am writing. So I am just solving this to get this, okay? So now you see that Vp comes out to be minus V out upon beta Rc into Rb plus R pi is what I have written actually already. Directly I had written that. Nothing but this, right? So please take a note till now, till here, and then we will proceed. Okay, so now we have got Vp, hmm? got Vp, which is V out upon beta Rc into Rb plus R pi. So there won't be this negative sign, won't be there. Okay, this negative sign won't be there. Okay, so now after this, if you put a KCL equation at node P, you will get V pi upon R pi plus GMV pi is nothing but Vp minus Vn upon Re. Okay. Now here you have to substitute the value of Vp and then derive in terms of V out by Vn. So I am giving you 5 minutes. Please try to solve it. So I was silently doing it so that I can find out if you guys are also able to do or not. So I've solved it and I'm coming with this answer of voltage gain. Please check it with your answer. Okay, if you have not solved it, then I'm giving you 5 minutes. Just solve it and check if you are getting this. And then once I will go through the entire solution. Okay, so I'm giving you 5 minutes. By 5:30, we'll resume again. Now you can see that uh, both C and CV stage they exhibit the similar voltage gains. Okay, so the difference comes from the input impedance and output impedance. Okay, so how I had solved it? It's the same way. We found out Vp, and we had another equation of V pi, right? So let me just put it in box. So this was V pi, and here we had Vp. Okay, and with this we proceeded the solution, and we put V pi's value in this equation which we found from Vp. Okay, with the KCL load at P. And when you put the value, you will and solve it, you will come here with only one assumption, that 1 plus beta is approximately equal to beta. That is the assumption we are taking, and finally you will arrive to this. So I am just putting the screen for 1 minute, so that you guys can see the entire solution, because this is a bit tricky. So if I put the entire solution, you might not be visible to you, so let me just put it like this. I think now it will be visible properly. Yeah, so I'm giving you 1 minute so that you can just go through it. Okay. Okay, so now let us see what is the input impedance B with the presence of, sorry, so I was mute. So now let us see what will be the input impedance in the presence of RB, and that is an interesting result. Okay, so let us derive that. I'm going deliberately going through the derivation and giving you a bit of time, because small signal model can be sometimes be tricky to derive and solve. So that's why I'm giving a bit of time for you guys to solve it as well. So let me draw the small signal model once again so that we can find out the input impedance. Input impedance will be the impedance seen with this source, right? So Vx by Ix. Okay, so please draw this. Then we will, and then then write what is V pi in terms of Vx. What is V pi in terms of Vx? Okay, please write that. Draw this model and write that. So I think you have drawn. So V pi is nothing but what? V pi is one of the voltage of a series combination of resistor. So basically, what I've drawn is this RB, R pi, and this node is V pi, right? So you can easily put voltage division and you can find V pi. So what is V pi? V pi is R pi upon R pi plus RB. I think there is no doubt here into Vx. Please see. After that, put the KCL at input node. Okay, put a KCL here and KCL at node X. Let me write this node X and just write the equation. Then I will write it and you can cross check. So KCL at node X will give you V pi upon R pi plus GMV pi equals to minus Ix. You can check. So Ix is the incoming current and V pi by R pi. So V pi by R pi is one of the current which is coming from here and the other current is GMV pi equals to minus Ix. Now in V pi you can put Vx, right? So V pi common. Let me write 1 plus Gm R pi by R pi equals to minus Ix. Now okay, so there is a minus sign here which I missed, minus R pi. Okay, so now this is Vx. Okay, so now V pi is nothing but minus R pi by R pi plus RB into 1 plus Gm R pi upon R pi equals to minus Ix by Vx. Minus sign gets cancelled. R pi gets cancelled. So therefore, Vx upon Ix is nothing but R pi plus RB upon 1 plus Gm R pi. Now Gm R pi is nothing but beta. So Vx upon R pi, which is Rn, is nothing but equal to R pi plus RB by 1 plus beta. Please have a look. This is an important result. From here gate questions can be asked. Okay. And you did not do all the solution for that. Since you now know the result, you will be able to directly solve it and we will see it how we do that. Okay. So please go through the solution once and then I will show you. So I hope that this is pretty clear, whatever I'm doing. Okay. So for a common base, what we have found out, Rn is nothing but equal to R pi plus Rb with the presence of a base resistor by 1 plus beta. This can also be written as approximated as 1 by Gm plus Rb by 1 plus beta. Hmm. This is also an important result. So both of these results, these are the same thing, right? And these are important results and it can be used in the GATE exam. Okay. Now please write down this result and then I'll draw one conclusion circuit which you can always keep in your notebook and keep it in mind. And after that we will solve problems. Please take a note of this. So now what we have seen is that for a common base, if the input is here, Va is infinity and there is a base resistance Rb, in this case we have, if we see from here, we get Rn as 1 by Gm plus Rb by 1 plus beta. So Rb is decreased by a factor of beta and gets added to 1 by Gm. When Rb is not there, it is only 1 by Gm which is present in the circuit, right? That we had earlier seen. But if Rb is there, a portion of the current also goes to the base, which is very small, and therefore the increment in the resistance is also very small, which is Rb by 1 plus beta. But in the common emitter case, the Rn that you see, so Rn is nothing but R pi plus 1 plus beta Re. And it doesn't matter if RB is connected or not, RB is here somewhere, right? And you have to see R in front here. So this is what the difference is. So C has higher input impedance than CB. So this is one conclusion that we can draw, and this is for remembrance. Okay, this is, you should remember. Okay, and please remember both these formulas, these are very important, and now you know how to derive them. So now please write this up, giving you 1 minute. After this we will solve the example problem. Okay, I'm not having much of battery left, but I hope we'll be able to finish. Just 1 minute. Okay, please take a look into all these results. Okay, so here is the circuit that you have to solve. I'm giving you the circuit. After that, I'm giving you 2 minutes. Please solve this. Okay, we have solved similar circuit when we were doing the common emitter thing. So we have two transistors. So can anyone tell me what are the configurations? So the first one yani Q1. Okay, so Q1 is a common base, right? Now what is Q2? Q2 is common emitter. You have to find Rx, and you did not solve the small signal model for this till now. If you have uh, concentrated in whatever was going on, you won't need small signal model for this, and this kind of question can definitely come in GATE exam. Okay, this can be topics. So this Q1 is in CB, Q2 is in CE, and now please solve it and find Rx. Okay, then we'll resume. So I'm giving you 2 minutes. It is enough for 2 minutes is enough for this, because till now whatever derivations we have done, if you have understood it, you won't need 2 minutes for this, right? Please solve it. Okay, your 2 minutes are up. So anybody, for this, in two steps you have to do. Okay, first, what is the resistance seen from here? Let us say this R equivalent. What is the resistance? So we have seen that for a common base, the input is emitter, right? This is the input. So R equivalent is nothing but R in for CB, common base Q1, common base biased Q1, right? So just now we saw that R in for a common base will be what? In presence of RB, RB upon 1 plus beta plus 1 by GM. This we just found this out, right? So this is what the R equivalent is. That it's nothing more than that. Okay. Now again you have to find out Rx, but now this is a common emitter configuration, and what you are seeing R equivalent will be treated as the R before that, right? So now there is a punch here that whether this is a common emitter or a common base. So I have written a common emitter. This can be a common base as well. So I was just looking into the question, and yes, this will behave as a common emitter, not a common base, not a common emitter. So this is my mistake, I'm sorry. So this is common base, because here in emitter there is nothing connected, and from here there is a DC biasing, there is no AC signal coming in. So considering this is a common base as well. So now what is Rx? So Rx will be nothing but R equivalent upon 1 plus beta plus 1 by Gm, and R equivalent is given by the one above. So if I consider Q1, Q2, this will be GM1, this will be GM2. Okay, so I hope now it is clear. So I'm sorry, that won't be common emitter, that is common base only. Okay. So just give me a few seconds. Okay. So now after this, uh, suppose I have a circuit like this. Now, can anyone see what is the problem with this circuit? So the problem with this circuit is that the emitter won't be DC biased, right? No DC biasing in emitter. The current doesn't have a path to ground. Okay. This design does not provide any DC path for the emitter current. Okay, and therefore the bias current is zero. And if the bias current is zero, the transconductance is zero, and therefore there is no gain. So normally how we bias a common base and put the signal is like this. What we do is, my iPad is becoming a bit slower, so just one second. Okay, so what we do is like this. So we put a capacitor Vn, and here we put a resistor Re. Now with this there is one problem. We now saw that the input resistance seeing here will be 1 by Gm. But here there is one more path of Re, right? So the current that comes from Vn, it distributes between 1 by Gm and Re. So basically Rn is now 1 by Gm parallel with Re. You understood the problem. So now Rn has reduced further. So in this case what we do is we try to keep Re very greater than 1 by Gm, so that the entire Rn turns out to be 1 by Gm and our circuit behaves in the way that it should behave. Okay, you understood? So this is one concept, and with this, if you have now, there will be one Rs as well, right? So there can be a source resistance as well, Rs. So with this, what comes out is, if I consider this point to be Vx, I will get Vx equals to Rn upon Rn plus Rs, right? Rn is 1 by Gm parallel Re into Vn. Okay. So with this, if you put in the values Vx upon Vn, you will get 1 by Gm parallel RE. This is what my Rn is. 1 by Gm parallel RE plus Rs. Now, if you open it, we'll get Vx upon Vn as 1 upon what you will get. There will be a 1 plus Gm Re term, right? So 1 plus Gm Re into Rs. Right? So therefore, V out by Vn is nothing but Gm times Rc upon 1 plus Gm Re Rs. Just have a look into it. I'm giving you 1 minute. See, compare what has happened with the presence of Rs. So I hope this is clear now. I will now do one question, which is again a kind of a design problem only, but things will get a lot clearer. Design a CB stage for a voltage gain of 10 and an input impedance of 50 ohms. Assume So the drop across RE will be if the current which is flowing through RC is IC. So I'm considering the drop across RE will be REIC. Okay. So please note this question down. I'm giving you 1 minute for this. After that, we will start solving it. We have to go step by step in this. Okay. So please take a note of this first. Please try solving the problem. I will solve it after that. Okay, so in this problem, we have to design the common base stage. Okay, so the details are given. So now what you have to do is, first you find what is the value of Rn. So we know that Rn is approximately equal to 1 by Gm, which is given as 50 ohms, right? And therefore, you can find IC, which is 0.52 milliampere. Okay, now before this, we have to select a value of Re. So approximately a good value of Re can be 0.5 kilo ohms. Okay, and once you have the value of Gm, you know the value of IC. Okay, because Gm is IC by Vt, so you know the value of IC. So first thing you have found out. Okay, now AV voltage gain is Gm times Rc. Okay, and the voltage gain of 10 is given. So Gm we know it is 50, 1 upon 50, right? And then you have Rc. So a good value of Rc will be 500 ohms according to whatever the data is given. So you see the value of Rc and Re is close, right? And now the voltage drop across Re. So voltage drop across Re is equal to 0.5 K into 0.52 milli, which is nothing but 260 millivolts. Okay, now to find out VB, you know the formula VT natural log IC by IS. So I am just running through this because we have very less time. Okay, and you already know these kind of steps. So just see whatever I have done till now, till here. Okay, please have a look. After that, I will show you the rest of it. So this is your circuit. Please remember your circuit, right? And this is what we have solved till now. Okay, okay, so now till VB you have got. So if VB you have got, then VB you can find out because VE you have, VBE you have. So VB is nothing but IERE plus VB. So that was the reason to find out IERE first and VB. So IERE we just saw, right? Here we have seen. So RE we have taken to 0.5 kilo ohm and IC we have got to 0.52. The same things we will put up and you will get 1.16 volts as VB. Okay, so now as a rule of thumb, you know that we take the current through R1 and R2, which is basically we denote it with I1, right? I1 to be approximately 10 times IB, right? So with this, if you proceed, this will be 52 microampere, and therefore VB approximately equal to R2 by R1 plus R2 into VCC. This we already know, and I1 we know it is VCC by R1 plus R2. Right, so if you solve these two, you will be getting, so I'm leaving it for you. R1 will be 25.8 K and R2 will be 22.3 K. Now a new thing here is that there is a presence of C1 in the circuit and we have to now find out C1. Okay, so we have to find out C1, and for finding out C1 the procedure is like this. Okay, so we normally take the impedance offered by C1 omega to be approximately very less than 1 by Gm, so that the circuit behaves properly. So 1 by C1 omega is approximately taken as 1 by Gm upon 20. Okay, so that is C1 is nothing but 20 times Gm by omega. So now if the circuit is operated at 900 megahertz, you will see that you get a C1 value of 71 picofarad. Okay, and this is how the value of C1 is obtained. So have a look. Now similarly for CB, the rule of thumb is like this: 1 by 1 plus beta. You can solve and see it because CB will offer the same kind of impedance as RE. So, so it gets divided by the factor of beta, and this is equals to 1 by 20 by 1 by Gm, and CB comes out to be 0.7 picofarad. So this is particularly two extra rule of thumbs that I wanted to discuss. We won't be able to finish common collector because of lack of time, but I think this will do. So please have a note and you can ask me any questions if you want. So I think you will be able to do the emitter follower on your own, since I have already done common emitter and common base. And tomorrow I think you guys have exam. So for ECE, I think you have it in second half or something. So all the best for it. Okay, and keep your calm and give the exam. Don't lose your calm. Okay, be very patient, and you won't be able to solve each and every question. So whatever you can solve, just focus on it and solve it. So I think this one will be pretty clear because we have solved similar questions in past classes as well. So please go through everything properly. If you have any doubts, you can get back to me. Okay, so in case there are no further doubts, I'll wrap up the session. Okay, okay, so all the best for tomorrow. It was nice teaching you guys, and I also learned a lot of things. Thank you.